All right, so welcome back. In this lesson, we're going to start taking a look at another quirk of the gradient descent algorithm. We're going to be taking a look at an example where our gradient descent algorithm actually diverges and spirals more and more out of control. And also, we're going to be working through some more hardcore Python programming concepts. So I'm going to click in my last cell, and then I'm going to go change this cell from code to markdown here. I'm going to add a hashtag and say example 3. Divergence, overflow, and Python tuples. The function that we're going to be looking at in this example is going to be this one. It's going to be h of x is equal to x to the power of 5 minus 2x to the power of 4 plus 2. Forgot my closing tags in the end. There we go. Maybe add another cell below actually, or 2, 3, so that we're not at the bottom of the screen. And then I'm going to generate some data. As always, that's going to be my first thing. So I'm going to make data. And since this is example 3, I'm going to use x underscore 3 as my variable. And I'm going to use np linspace starting at minus 2.5 going to 2.5 and with the num argument set to 1000. Okay, so now it's time to write that equation above in Python code. So it's going to be df h of x colon return x times 5 minus 2 times x times 4 plus 2. And then our derivative of this function is going to be df d of h of x colon return, and then you've probably already worked this out by applying the power rule. It's going to be 5 times x to the power of 4 minus 8x to the power of 3. Okay, so let's plot this function. I'm going to scroll up and I'm going to take this cell here, say copy cell, and then I'm going to paste it above. Now I'm going to have to make some changes to this code. Over here with the gradient descent, we're going to be calling d of h, and I'm going to say my initial guess should be equal to 0.2. I'm going to leave a lot of the other stuff as it is, but I'm going to change my x-axis and y-axis on my graph. So this graph is going to go from minus 1.2 to 2.5, and the y-axis is going to go from minus 1 to 4. So that's our cost function. I'm going to change the y label to read h of x. I'm going to plot x underscore 3 on h of x underscore 3. And on the scatter plot, I'm also going to be plotting h of x, not g of x. Similarly, for my derivative, I'm going to change the label. And on the axis, we're going to go from minus 1 to 2, and then from minus 4 to 5. And then on the plotting, I'm going to change this to x3, dh of x3, and then I'm going to hit Shift-Enter. Voila. So we can see here on our graph, we start at positive 0.2, and then our gradient descent slowly makes its way down into this local minimum right here. Let's modify the cell here to print out what the values actually are. So I'm going to say print local min occurs at, and it's going to be local underscore min, and then I'm going to print the cost at the minimum is, and then I'm going to say h of local min, right? So local min, remember, is the last value calculated by our gradient descent. We're going to work out what the y value is on our chart here at this particular point. And finally, let's print out the number of steps that our algorithm has taken, including the initial guess. So that's going to be the length, len, of our variable called list underscore x. If I rerun this now, I can see the output here at the bottom below our charts. The local minimum occurs at around 1.6. The cost of this minimum is about minus 0.62, and the number of steps is 117. So our gradient descent algorithm has run over 100 times to get to this point. Okay, so we're converging to this minimum here, and so far, nothing new. We've seen all of this before. But let's see what happens if instead of at 0.2, we start at negative 0.2. Let's see what happens if we start a little bit on the other side of this chart. So I'm going to scroll back up, and here, where my initial guess is 0.2, I'm going to change this to minus 0.2, and I'm going to rerun the cell and see what happens. Scrolling down, we see an error. In fact, we see an overflow error where it says the result is too large. What does that mean? I'm going to change the initial guess back to 0.2, hit Shift Enter, reload the graph so we can think about this. If our initial guess was negative 0.2, then we would be on the left-hand side of this hump. And this means that the algorithm would be starting to move down and down and down and down this line here. Now it would continue going all the way down to like negative infinity. Now I know what you're thinking. Negative infinity. That makes h of x a very unrealistic cost function. But it does illustrate several things. First, we can see how our gradient descent algorithm behaves when the algorithm diverges. And second, it shows us how our Python program behaves when this happens. So conceptually, we've explained the problem. But I do think that seeing this overflow error gives us an opportunity for understanding something a little deeper about our Python code. So let's run our code in slow motion, if you will, and examine what's actually happening. And to do that, I'm going to modify our gradient descent function. So I'm going to scroll back up where we've defined our gradient descent. And in our function header, I'm going to tack on another parameter. This parameter is going to be called max underscore iter for max iterations. I'm going to give it a default value of, say, 300. And instead of this hard-coded 500 value here in our range, I'm going to substitute our argument. I'm going to substitute in max iter for max iterations. So this way, we can specify the maximum number of times our loop will run when we are calling our function. So I'm going to press Shift Enter to update the Python code now. So I'm going to update this cell, and then down here where we're generating this graph with our third example, I'm going to change our function call as follows. For our initial guess, I am going to use minus 0.2, but then I'm going to give a max iteration value of 10 and see where this leaves us. So I'm going to hit Shift Enter and take a look at the graphs. Okay, so in 10 iterations, we're still pretty much on this hump. If instead the max iterations of our loop are set to 40, then we can see we start moving a little further down. And if I change it to, say, 60, then I can see we're moving down even more. Now let me update this to 70 and rerun this function. When we examine the chart now, what do we notice? Well, yes, it's moving down to the left, but very interesting here, is that the step size gets bigger and bigger with each step. As this slope starts getting steeper and steeper and steeper, our steps start getting larger and larger and larger. So what's the last x value that the algorithm calculates? We're printing out the last x value with this print statement. So we can see below our graphs are the printouts from our 3 print statements. We can see that the last x value that's printed out is -2 million. That's the first print statement here. And this is definitely not a local minimum in this case. But when we feed our -2 million back into our function, then we can see that the cost, what's on the y-axis at this point, is equal to -3.8 times 10 to the power of 31. So in our print statement here, Python is giving us this number in scientific notation, but it's actually an enormous number. It's around 380,000,000,000. It actually continues going, right? I'd have to copy this, paste it 3 times. This is how large this number is that's being printed here in scientific notation. It's 3.8 with a lot of zeros after it. But yeah, I mean, you're going to be looking at this number and you're like, well, it's a computer, right? So what? We sent a man to the moon over like 40 years ago. Surely my computer can handle calculating large numbers, right? What's the big deal? And you're not wrong. We can and we should be able to do math with very large numbers. But the thing is, your computer and Python doesn't do this straight out of the box. If you want to work with numbers of this sort of magnitude, if you're, I don't know, calculating the number of atoms in the universe or what have you, then you have to employ a couple of tricks. The thing is, you can actually see what the maximum is that you can reach on your particular machine at home right now in Python straight out of the box. And that's without importing any libraries or any modules and using Python as it is that you've got installed right now. So if you're curious and you wanted to pull up this sort of system-specific information, you can actually do so with a module called sys. So import sys. Sys is the module where the system-specific information resides. And there you can pull up a number of different things. To see the kind of things that I'm talking about, you can write something like help and then put sys in there, and then you'll get some documentation on the system module. So you can read this. This is, by the way, very, very similar to what you can pull up by pressing Shift and then Tab, and then hitting that little plus sign. You'll see that this also pulls up the same documentation. But let me show you 2 things that might be quite useful. I'm going to comment out the help here. Don't need this. So for example, one thing that you might be interested in looking up is what version of Anaconda you're using, or what version of Python. And you can pull this up by writing sys.version. So version is an attribute of this system module. So right now you can see that I'm using Python 3, and I've got a 46-bit system. And you can also see that I'm running this on a Mac. Let me comment this out again. And let's look at something else. Let's pull up what the largest floating point number is that I can calculate in my Python program. Now you might ask, why am I interested in floating point numbers? Why do I say floating point numbers? Well, if you have the type of the thing that we're looking up, right? The type of thing that we're calculating, h of, take a look. In this case, it's h of local min. So this is the thing that gave us the problem. So this is a float, and this is what we're looking up. The largest float that we can use is sys.float_info.max. And here's our answer, right? And this number that you see printed out here is specific to my machine. If you're using a different type of machine with a different architecture, say 32-bit, then you may see something else printed below the cell right now. But this is my maximum floating point number that I can use on my architecture. Yeah, it's 1.79 times 10 to the power of 308. Yeah, this is huge. But it's still well shy of the 10 to the power of 31 that we had just a moment ago, right? It's many, many orders of magnitude larger. So you might ask, why are we running into this problem? Well, looking at our chart, we can see that our step size increases dramatically with each step. And if I go up here and I change this from max iterations, the number of times I run my loop, from 70 to say 71, and I look at my cost, then I get minus 2.1 times 10 to the power of 121. So this is the crux of the problem. I'm going to blow through my limit at the very next iteration, on iteration 73. This is when I get the overflow error. Now on your machine at home, if the number that you're seeing printed here, the number that's spat out by sys.float_info.max is smaller than this, then you might actually get that overflow error much sooner than I do, right? You might not get it at iteration 73. You might actually be getting that error far earlier, that overflow error. Now, one thing that you might like to know about Python lingo is that errors like this are also referred to as exceptions. But yeah, no matter if you call it an exception or an error, we still crash and burn. So yeah, I hope you enjoyed that little detour into the low-level representation of numbers inside your Python computer program. But I think that while we're on the topic of Python programming, we should revisit a piece of code that we've written in a previous lesson, namely the code up here. The code for our gradient descent algorithm. Because I have to confess something. I've been a little cheeky in having our Python gradient descent function return multiple values without actually explaining how this works. And this is a good point to cover the Python code before we go back to actually analyzing our algorithm. So let's add a new section heading at the bottom. I'm going to click this little plus sign here to insert some cells below. And this cell here, I'm going to convert from code to markdown. And the section heading I'm going to give this is Python Tuples. So what's a tuple? A tuple is a data structure that's very, very similar to a list. A tuple is just a sequence of values that are separated by a comma. And this is what we've used in our gradient descent function. Let me show you how you can create a tuple. Click plus again here, and let's do this. Let's insert a quick comment here. Creating a tuple. My first tuple is going to be called breakfast. And it's going to contain 3 values: bacon, eggs, and avocado. This, by the way, is a fantastic way to start your day. And it also illustrates the general format for tuples. You have a sequence of values that are separated by a comma. I'm going to create another tuple here. Call it unlucky underscore numbers. And we'll give it 13 for China, 9 for Japan, 26 for India, and I think 17 for Italy. So it's the same pattern as above. And this way of creating tuples actually has a name. This is called tuple packing, because we're packing multiple values into a single tuple. So now that we've got our tuples, how do we access them? Well, I'm going to add some print statements here, like I love, comma, breakfast, square brackets, 0. I'll hit Shift Enter. My lack of spelling ability has foiled me once again. I'm going to take out the superfluous E here and hit Shift Enter again. And there we can see that the syntax, with the square brackets for working with tuples is actually very, very similar to working with a list. So you've got a tuple that has a name, in this case breakfast, and you're accessing the values inside the tuple through the index. So 0 is the first item in the tuple. And to show you a second example, I'm going to print out the string my hotel has no space, and then I'm going to have 2 plus signs, another string at the end, th floor. Now in between here, I could put unlucky underscore numbers and then square brackets and say provide the index 1. And if I try to run this right now, I'll get an error because the string concatenation with the pluses does not convert the integers here to strings. So I have to actually wrap this in a function called str. And only now can I press Shift Enter and run this. If I try to do this without wrapping it, then you'll get an error like this. Must be string, not int. And that's because my tuple here contains ints, and those are not converted to strings by the plus operator. So I'm going to wrap this in a string function and press enter. So we've covered how to access a value in a tuple. Brilliant. Now we can try something else, because I'm sure you're looking at this and you're saying, well, how are tuples different from lists? How are tuples used? Why do we have something that's so similar and yet different? Well, in contrast to lists, tuples are often used when the data they contain is heterogeneous. Now, what do I mean by that? Tuples often contain a mix of data in contrast to lists. So lists often contain the same kind of data, like all strings, all integers, but a tuple, like say not underscore my underscore address equals 1, comma, and then the string infinite loop, and then comma, and then another string Cupertino, and then comma 95014 for a postcode. Then we've just created a tuple with a mix of data, a mix of different data types, if you will. And this is something that you don't usually see in practice with lists. Lists are usually homogeneous, meaning people don't tend to mix and match the different types of data. Now, another difference with lists is that tuples are immutable. What does that mean? It means that we can't change the tuple after we've made it. So, for example, if I had, say, breakfast, and I wanted to change bacon, which is at index 0, and set that equal to a, say, sausage, and just, innocently swap out the value, then Python will actually yell at us. It's going to give us a type error. It's going to say the tuple object does not support item assignment. And this basically means that once we've created a tuple like this, we cannot change the values here. And we also can't append a new value. Say we can't stick this at, say, index 3, right? We get the same error. In other words, the immutability of tuples means that once you've created a tuple, you can't mess around with it. You can't change it up. And this is quite different from a list, right? Because if you remember in our gradient descent function, we were running our loop and we were appending items to our list. So every time the loop ran, our list grew in length because we were appending new items. And this is something we couldn't do with tuples. Now, one more thing I want to show you on the topic of tuples is a little gotcha. Say we want to create a tuple with a single value. So just one value inside our tuple. I know it's strange, but for the sake of argument, have a think about how you would create a tuple with just one value. What would the Python syntax look like to store a single value inside this tuple? Here's the solution. So if I put a single value in here, say 42, then I would have to put a trailing comma after it. Now I've got a tuple with a single value. So if I print it out, print tuple with single value, then I can see it looks like this. It's got a single value and a comma. And if I substitute the print for type and check, then I can see that indeed tuple with single value is indeed a tuple. Now, the very first time I saw this, I found this syntax like super weird and confusing. Trailing comma, right? My goodness. So here it is. Now, you too have shared this experience and the weird syntax. You're welcome. Now it's time to come full circle. We've packed a bunch of values into a tuple, but we can also do the very opposite. So we can unpack these values as well. So if I take my tuple, breakfast, yeah, and I want to grab the values that are stored inside this tuple and put them into some separate variables, I can do that by writing, say, main, comma, side, comma, greens is equal to breakfast. And this is called sequence unpacking. Yeah. So if I print out main course is, and then comma main, then I get main course is bacon. So here's the reason I mentioned this and why I say we've come full circle. If I scroll back up to where we had our gradient descent function, we can see here in our return statement, what we're doing is we're returning 3 separate values, but in fact, we're packing all these values into a single tuple. Yeah? And when we're calling our gradient descent function, say here, then we are unpacking this sequence and storing the results in 3 separate variables: local min, list underscore x, deriv underscore list. So we've actually been using tuples, but we've never had to access any of the values from the tuple by index. But we can do that. Let me show you how it would work. So if I created a variable called data underscore tuple and set that equal to gradient underscore descent, and for my derivative underscore function, I supply dh, and for my initial guess, I supply 0.2, then I can print out the local min at data underscore tuple, square brackets, 0, because that's the very, very first thing that is stored inside our tuple. I can print out the cost at the last x value, which would be equal to, well, in this case, it would be h of data underscore tuple, square brackets, 0. And then I could also print out the number of steps, which in this case would be the length of, so it would be data underscore tuple, square brackets, 1. Let me run this. And then you can see that it works exactly the same way as before, but instead of unpacking the sequence, we're using the tuple now explicitly. Okay, so we've paused a little bit on analyzing our algorithm, and we've talked a little more about Python and Python programming. So now it's time to change tracks and go back to our gradient descent algorithm. Now, a reasonable question to ask is, why did I show you this h of x example function? I mean, this function, by my own admission, seems a little bit contrived. And I already confessed that a non-convex cost function is not very realistic. But truth be told is that we can get this divergence and the very, very same overflow error in another way too. And we can see this divergence and see the same error even if we are working with a very nice, clean cost function, where we know for a fact that we should be able to reach a minimum. And this is what we're going to be examining in the next lesson. In the next lesson, we're going to be looking at the elephant in the room, the gradient descent learning rate. I'll see you there. Take care.